recording, but yeah, I started now. So all these activities as we'll have tonight are available on our YouTube channel. Okay, as I mentioned, we have our conference, our annual conference. This is the second edition of it. Is coming on the 26th to 28th of November. Preparations are in full gear, and we hope that you are as excited as we are. The speakers are ready. You can see on the screen that we'll have several programs that are already outlined. These are the highlights, but there are more programs behind the scene. I tell you, you wouldn't want to hear as a story. So please join us. Keynote speakers have My Career, My Story, How I Became Me in Career and Influence. We have 3 speakers who will be speaking from different perspectives. One will be speaking from the perspective of an African scientist who did the career within Africa. The other will be speaking as an African woman scientist. And we'll have a speaker who will be presenting from the perspective of an African scientist in diaspora. So please do not miss these sessions. And we'll have panel discussion that will be looking at ethical innovation, respecting the respectables. And the boot camp, we have 2 workshops that will be happening. Just to let you know, registration is ongoing, and the early bird registration ends tomorrow. After tomorrow, then it will be late registration that starts. So please take advantage of the next 24 hours or so. So please do that. And then we have the late breaking abstract. If you have not submitted, it also ends tomorrow. So please take advantage of this and get yourself ready to join us in this event we are looking forward to. Now, having had a very successful first edition of the ASFI time, we are going again with another edition, the second edition, coming up on the 11th of October. This program is organized by the ASFI Members Assembly. So they have put this up, and we encourage every one of you, please come. It's 1 hour engagement in discussing topical issues that are around the corner. And I hope that you would endeavor to not only join yourself, but also to bring others to join. There's a registration link which has been circulating, and I believe that you already start to join. Okay, as I mentioned, one of the hands-on trainings we have, the Art of Scientific Writing and Publishing. This is actually something that many researchers struggle with. Yeah, to be frank with you. And we can see that even as an organization, having launched a ASFI research journal, we can see that many scientists require support. And so ASFI provides this. This is one of our signature trainings. And so please, the application ends on the 11th of October. Take advantage of that to register yourself, and the course will run from 19th of October to 21st of December. It's only Saturday evening course, so that you can do it in a relaxed manner without having to worry that it is affecting your work schedule. All right, so please raise and join us. And then we have the journal I mentioned. We have launched. As you can see, the papers that were submitted in the maiden issue are being published currently. And it's exciting that our dreams have come true in this regard. We promise you is a platform that will stress excellence, will stress quality, and we will aim to publish impactful research. This promise we will keep. So we have assembled a team of not just experts in their various fields, but those who are passionate about development of Africa. So please, we invite you, submit your papers. Every paper submitted in the maiden edition is being published free of charge. But the journal, as you know, this is a business that requires resources because we want to create a platform that everything that is published is made freely available. People can use it from any part of the world. They can cite it, they can download it. So it's purely open access. And to do that, to archive it, to support the team that is doing this behind the scene, ASFI Research Journal takes very, very minimal article publication fees, very minimal. So yeah, that will be a way of supporting the move and the vision. For you who are ASFI members, usually you will have up to 50% discount in publishing, as it is with every other ASFI program as a member. We mean business here, and those who have gone through the publishing process, I tell you that we do not just publish anything. At least up to 60% of the papers submitted in the first edition, in the maiden edition, were rejected. So we stress excellence, and those who have gone through, they see the quality of review, the quality of the editorial staff, because our goal is to uplift Africa and put ourselves where we belong. Yeah, the long story is to encourage you. Please bring your papers on board. We welcome them. And we have different types of papers. We publish original papers, expert reviews, systematic reviews, perspective papers, protocols, editorials, commentaries. And saying about commentary, I have to stress this because many of those who are in the ASFI platform are young scientists. And sometimes you are really overwhelmed of how to get started with your scientific communication, telling your story to the scientific community. One way you can do that gradually is to write commentaries. So you can go to ASFI Research Journal website, look at the papers, look at interests, those that interest you. You can write a commentary and send to the editor about the paper, and then we'll look at it. It's quite easy to get published as far as your commentary is meaningful. So it's one way to get started. All right. So we have other papers like editorials, research letters, field stories. Sometimes you see you are having very interesting stories, weird stories, surprises, and things that happen in the field, maybe in the lab, maybe outside, it may be in the environment, it may be during your interview, things that just come up and you would like to share it with the scientific community. So please bring them on board. We'll have opinion papers and so on and so forth. So it's quite a wide range of things you can do. And finally, it is a multidisciplinary journal. So whether you are in engineering, you're in medicine, you are in the humanities, you're in the arts, you're political, so you're a theologian, it doesn't matter. We publish papers from any field. It's a platform you would like to, I trust you, you would like to publish your papers. Okay, this year is about innovation, and this is quite important because without engaging in innovative research, then it's really, to say the least, a wastage of time doing research, because it needs to be innovative. You need to identify societal challenges and provide solution to them. And this is the UNESCO mantra that science is the greatest collective endeavor through which we can have basic needs of life. And if it ends up not addressing basic needs of life, it becomes an academic exercise. So it needs to provide these basic needs for it to be meaningful. And Africa has numerous problems across board, different challenges that we face, and innovation and research becomes important to guide us through overcoming these challenges. I've defined this quite often. I like the University of Oslo definition of innovation. It says it's new ideas that work. What do they work? They provide solutions. Innovation consists of processes that lead to a new or improved product, or measures that will improve services or solve societal needs. Innovation is about adding value to society. This is what we are doing this year. So we're about to start. Some of you are already doing it. Please use the chat box to introduce yourself. Tell us where you're coming from. Tell us what you're doing. Many people get collaboration through this platform as well. And then, of course, once the speaker starts, please write down your questions on the chat box. We're collecting them behind the scene. And once the speaker finishes his speech, we're going to showcase them on the screen for him to answer the questions. All right. So this evening, ladies and gentlemen, I want to present you the speaker for tonight's seminar, Dr. Noel Jobo. He is a distinguished chemist and researcher and specializes in low carbon construction materials. He's currently a research associate at Imperial College London. I know that is one of the, I think the top 5 to 10 best universities in the world. So getting there indicates the importance of what he's doing as a researcher. His research work focuses on developing sustainable building materials that will help to address the global challenges of decarbonizing the cement industry. He completed his PhD in 2017 from the University of Yaoundé 1 in inorganic chemistry, specializing in the physical chemistry of mineral materials, which helped him to lay the foundation for his future contributions to sustainable construction. Throughout his career, Dr. Jobo has dedicated his time to development of innovative, low-carbon building materials. His research primarily involves processing abundant natural resources such as clay, volcanic rock, and lateritic soil to create materials with tailored properties. These materials are designed for various applications, including insulation, natural cooling of buildings, energy storage, and cost-effective infrastructure in low-income countries. His contributions to the field include the development of low-carbon cements, such as ternary and blended cement, as well as alternative cements like geopolymers, alkaline activated materials, phosphate cement, and magnesium silicate cement. He has also worked extensively on earthen-based construction materials, including stabilized, compressed earth bricks, and earth concrete. His notable achievements have been recognized with several prestigious awards, and this include the World Academy of Sciences, Council of Scientific and Industrial Research Postgraduate Fellowship, the Alexander von Humboldt Postdoctoral Fellowship, and the Marie Curie Postdoctoral Fellowship, which he eventually declined to take up. He's an affiliate fellow of the African Academy of Sciences and a member of the International Union of Laboratories and experts in construction materials, systems, and structures. In addition to his research, he's actively involved in academic publishing and peer review. He serves as an associate editor for the Journal of the American Ceramic Society, a member of the Independent Review Committee for PANACEA RSIF PhD scholarships, and reviews for several high-impact scientific journals. His work has been widely published with numerous peer-reviewed journals to his name and an H-index of 23, according to Scopus. His dedication to addressing global challenges is evident in his role as expert reviewer of the IPCC Working Group 3 for the 6th assessment report. He is also a passionate educator and mentor with supervision of several PhD and MSc students, and his role as a mentor at Imperial College London. Dr. Jobo's pioneering research and commitment to sustainable construction materials continue to make significant impacts in the field, contributing to the global effort towards a net zero built environment. Ladies and gentlemen, please join me to welcome our speaker for this evening, Dr. Noel Jumbo, who will be speaking on the topic, Sustaining Africa's Buildings, the Power of Volcanic Ash. Some of you are hearing it for the first time as I am, so I am excited, waiting to hear what tonight holds. So, Dr. Jobo, the floor is all yours. Thank you.
Okay, thank you so much, Professor Bright, for this nice introduction. I'm very happy to be here and to share this piece of information and knowledge with all my African fellow. It's quite a big pleasure to be here. I will be talking on the sustaining African building and how one of our natural resources can be useful for us to achieve sustainability in the built environment. I will introduce my with this that is the built environment, and find the built environment as physical and social infrastructure that surround us, that encompass like all structure, space, the construction of commercial building, road, and I-house building too. As you can see from this picture, that is how we need our built environment to look like. But to be able to achieve this, the built environment is known as one of the primary end use of high impact material. So it consumes a lot of material. And the challenges with all these consumption of raw material is the carbon footprint of the built environment. It's nowadays correspond to about like 42% of the annual global CO2 in the world. And this CO2 emission of the built environment can be split in two types of emission. We have like the operational carbon emission and the embodied carbon emission. What we mean by operational carbon is anything related to functioning the building, the electricity that you need to in your building, the heat needed for heating the energy needed for heating the building, and also the energy needed for cooling the building, specifically in Africa where the temperature is a bit high. So all these account for the operational carbon. And the second type of emission is the embodied carbon, which is one of our main interests for this talk. And the embodied carbon encompasses everything related to manufacturing the building material. So This means extraction of the raw resources, processing the resources, and their transformation to the different type of construction material. But the point is that we are all aware about the changes in the all the changes in the climate because of the all human activities. But in 2021, the embodied carbon represented like 25% of the whole carbon emission of the building. But many effort has been made so far to reduce the operational carbon. So now the plan is how can we improve the embodied carbon? And because if nothing is being done, this embodied carbon is expected to rise to 40, almost 50% by 2050. Africa, the built environment in Africa has many challenges. Africa is the continent with the fastest urban population growth in the world. And by 2050, this will represent almost 3.17%. And this means that the population in Africa will triple by 2015. So we expect the population to increase by almost 1.3 billion people. And the 10 world growing city in Africa by 2035 are expected in the world are expected to be in Africa. Because of that also, we need a lot of infrastructure to accommodate all those populations. And the point is that so far, the amount of building needed for Africa to accommodate that rapid growth of the population, the rapid urbanization by 2050, we have 80% of the building material that Africa will need by 2050 are yet to be built. So this means Africa will consume a lot of resources to be able to build infrastructure, houses, and everything for its population by 2050. The point is that the population of the Africa, as we can see in this graph, is almost scattered all over the different regions of the continent. And the resources that we need to build all the infrastructure by 2060 will mainly increase the amount of carbon emission that Africa is using. But the point is that actually only 2% of the globally produced cement in the world are produced in sub-Saharan Africa. So Africa is bigger than Europe and North America putting together. And in those countries, 80% of the population are already living in town and city. But in Africa, many population are still living in the rural city. But because of the development of the different African countries, we expect that population to rise very quickly, and we need to find a solution to accommodate them, as I was saying previously. What happened is, in Africa, the consumption of raw material and all the environmental issue related to the production of the raw material draw the attention of the scientists that we need to find solution to be able to develop our continent without impacting our environment. And the three principles for enacting the decarbonization of the building material rely on these three words: avoid, shift, improve. We mean by avoid, while we are developing our continent, we need to avoid extracting the new resources. We need to rely on waste material, try to reuse them and deal with like a circular economy system. But where the waste that can be turned in sustainable building material cannot be found, like in many African countries, another principle rely on shift, which means if we are not able to to use waste, if you are not able to deal with the circular economy, another alternative is to shift the type of raw material that you are using. We can rely on bio-based building material like earth, building material, timber, and bamboo. And the third principle is improving, which means concrete, for example, is known as the second most used, most consumed material in the world after water. And the concrete is made when you mix cement, sand, and aggregate. But cement in concrete is the most carbon intensive material. And we need to find a solution to mitigate it. And the improved system means, since cement is a material that is used worldwide and it's a very useful material for building the infrastructure, because of the embodied carbon of the material, we need to find a solution to overcome it. Let's delve into the cement production and why we believe that it is a carbon-intensive material. Here is the process how we can develop how cement is produced. Initially, for making cement, you need limestone and clay. And the limestone deposit and the clay deposit need to be put very closely so that the production can be efficient and beneficial for the company. When limestone and clay are extracted, they are now being crushed and milled to get fine powder. And that fine powder can now be calcined using a rotary kiln. And here is where most of the issue related to the carbon emission of the cement happen, because here you have when you calcine clay and limestone, you see limestone has like some carbon CO2. So this will release a lot of CO2 in the atmosphere. And the point is that the energy used for calcining limestone is also problematic, because in general, people use like fossil or fuel energy. And this clinker, when you calcine here, the product that you have is called clinker. Now you just mix clinker with gypsum, you have your cement. Here is the Portland cement bag that we can find in the market everywhere. And that product now need to be transported to different places. This whole process emit a lot of CO2, as 1 ton of cement will release about 0.8 or 1 ton of CO2, which is quite a lot. And when we consider the amount of concrete used around the world, it comes that cement alone contributes for 8 to 10% of the global emission, which is quite huge. And in Africa, actually, we are consuming less cement, but to be able to achieve our infrastructural need, we will consume more cement in the coming year. So knowing the different impact on the climate change in the environment, the strategy adopted now to decarbonize the cement worldwide, I mean, this is a strategy that is accepted by the whole community, by the whole cement industry, and rely on 3 methods. The first method is the carbon capture and utilization, which means we come at the cement plant, we set up a device or a kind of machinery that we capture the CO2 that is being released during the calcination, and that CO2 can now be stored on the ground like a geological storage or used for something else. But the point is that a lot of technology are being developed in that sense. But I mean, we all know that there is an issue with the cost and the price of implementing that technology, although they seems to be efficient for capturing. The second principle relies on designing low carbon cement production technology, which means using alternative fuel for the calcination process, and either also trying to harvest the heat released during the whole cement production process and to reinject that heat to the process. This also requires lot of technology and lot of money, I mean, to be implemented, although they seem to be efficient in some point. The third method rely on designing alternative cement. What I mean by alternative cement is, since despite all the method that has been applied so far, we still have some CO2 emitted by cement. Whereas the world agreed that we need to achieve a neutral built environment by 2015. In the alternative cement, this means the Portland cement that I showed previously how it is being made can be replaced by some raw material. And it is known that if you replace a raw material like by 20%, if you replace cement by 20%, the balance will be like 20% of CO2 will also, 20% of CO2 released by the production of cement will also be diminished. So it means the higher replacement level, the higher carbon emission mitigation you can achieve. Among the two type of alternative cement that I will be talking to you this evening, we have first of all blended cement. This one is already being commercialized in the world and mainly in Africa. So to make blended cement, you just take the Portland cement that is produced as I shown previously, and you mix with what we call supplementary cementitious material, SCM. When you mix those two powder, you have your blended cement. So the supplementary cementitious material that is being used include fly ash, slag, calcined clay, and volcanic ash. In Europe and Asia or America, they mainly use fly ash and slag. In Africa, you will mainly see companies are mainly use calcined clay and volcanic ash. This material can also be used to develop a new type of alternative cement that is called geopolymer. Here, the principle is quite simple. It means you can use the same supplementary cementitious material that is being already used so far for making blended cement. You can use the same material to develop the geopolymer cement. And the second ingredient that you need for it is only an alkaline activator, which is in general sodium silicate. There are many of them, but this is like the mostly used one and the most accessible one. I just have to mention that this sodium silicate is a commercial product that is being used actually in cosmetic industry to make soap, detergent, and many other chemicals. So it is already well commercialized, and within the African continent, this is a product that's well known by many industry, and it's being produced in the continent. So to make geopolymer cement, it's so simple. You have your alkaline solution, and you mix with a raw material, which can be calcined clay, fly ash, or volcanic ash, to make your cement. So now, what do I mean by fly ash? Fly ash is a hazardous byproduct generated by burning pulverized coal in power plant. So in some countries where they produce electricity based on coal, they have this kind of waste material that's being generated. And in Africa, the only country, very few countries are producing this type of ashes. And the second thing is that although this material is like being produced in large amount around the world, and some countries are being producing, the point is that the transition that is happening actually in the energy sector make that now many countries are going toward solar energy or wind turbine energy or geothermal energy. So this type of product are being less produced. The second SCM is GGBS, which is granulated blast furnace slag. This material is produced while you are making iron and steel. So during the process of making iron and steel, you have this waste material. But the point is that as fly ash, this material also is not very well popular in the country, because very few countries, maybe Egypt and South Africa, also are producing this type of waste material. But also in the steel production process, all the effort that are being put there to transition from the high carbon emission steel to low carbon emission steel will we lead to the scarcity of this material. So we need to find alternative. Calcined clay is a very good alternative, but the point is that the SCM, the clay that is useful for developing blended cement or for developing geopolymer, you will also heard about kaolinite, which is a material that we are very common. It's also used for pottery or making ceramic and many products in the continent. So kaolinite can be calcined in temperature between 650 to 750, and we will get metakaolin. As I said, kaolinite is not like of course, we can find it around Africa, but among the different type of clay that exists, kaolinite is one of the least available one. So what we have as alternative is, of course, volcanic ash. What is volcanic ash? Volcanic ash is produced when the magma get out of a volcano during an eruption. We have, I guess everyone here has already heard about a volcanic eruption. And in the production of volcanic ash, you have the formation of magma on the ground by melting the different rock because of the high temperature. And when the eruption come out, the magma we try to escape from the volcano. And during that process, there will be the fragmentation of the earth or of the rock around the volcano, and this will create like a vague ash, as we can see in this figure. And those ashes, and that ash can be is generally deposited in the villages around, as you can see here. It means after a volcanic eruption, the villages and the agricultural land around it are generally buried by ashes, which of course is cause an environmental issue. And the second point is like that those ashes can travel in a very long distance. It is estimated that after a volcanic eruption, we can find the ashes in over 600 kilometers far from the volcano. Here is the world distribution of the different volcanoes around the different volcanoes. As we can see in Africa, we do have a lot of volcanoes almost spread out in the world, in the different regions of the continent. And as I was saying previously, even the country in Africa which do not have volcano, it is also possible to find volcanic ashes there because, as I said, the ashes after eruption will travel in many distances and very different lines. So it is quite an interesting material, widely available, specifically in the African continent. But what happened is volcanic ash look like this. You see, we have, depending on the composition of the material, we have I would say two types of volcanic ashes. We have volcanic scoria and we have volcanic pumice. And the scoria look like this. You have like a very highly vesicular material with very large pore, whereas pumice look like this with very teeny pore and very low vesicular material. So those materials, you can find them in different colors. So even volcanic scoria, you can find volcanic scoria with brown, red color. Even pumice can be found in black and different color. Their chemical composition, they contain mainly silica and aluminum and iron. But volcanic scoria is distinguished from volcanic pumice because of the amount of magnesium oxide and calcium oxide. So this composition is mainly what I characterize, because in Cameroon sometimes we analyze a very large amount of volcanic ash deposit in the whole country, and we have been able to find that most of the volcanic ash in Cameroon, for example, belong to the volcanic scoria category, where the volcanic pumice here are mainly found in European countries like Italy or in South America. So because of this Because of this characteristic, because of that chemical composition, volcanic scoria can also be used for making blended cement. But the point is that the scientists nowadays are saying that volcanic ash is not a suitable material because it has a low reactivity. In this graph, I'm trying to show the difference between the reactivity of volcanic ash and calcined clay. So here, when you want to make your blended cement, to know that your super blended cementitious material is a suitable material, you need to make a test which is called calcium hydroxide consumption or lime consumption. So because when you mix the supplement cementitious materials with Portland cement, and when you add water in the system, what happens is like that SCM will react with cement and it will make cement to be more stronger and more durable. So, but here when we compare the reactivity of the volcanic ash and calcined clay, it's clear that volcanic ash is very less reactive than calcined clay. That's why in many European countries, even where volcanic ash are available, they are not used as SCM. But in Africa, we do use them as SCM, but we generally add very low percentage. So because of that low reactivity, one of my work has been how can we improve the reactivity of the volcanic ash? The two methods that can be applied are the calcination of the volcanic ash and the mechanochemical activation. What I mean by the calcination is you can just take your volcanic ash and put in a furnace and heat up to 700 or 800 degrees to calcine it. But that is what is happening with clay. Because when we take clay in natural state, it is not reactive. But to make it reactive, you need to calcine it. And in the previous slide, I was trying to compare volcanic ash that had been used in natural state and clay that had been calcined. We have seen that the clay was very reactive. Calcined clay was very reactive than natural volcanic ash. So some of the work has included the calcination of the volcanic ash, but the point is that the calcination was not quite efficient because during the calcination, in principle, you have, in volcanic ash, you can also have some clay mineral. And during the calcination process, what happened is the clay mineral are being decomposed. That's what increased the reactivity. But since in many of the volcanic ash, the clay mineral are where they are available, they are very low percentage, like less than 2-3%. So calcination is not efficient. So one of our work rely on the mechanochemical activation. The process is you induce a chemical reaction by a mechanical process. So when you put volcanic ash in a ball mill, when the milling is happening, you have a process where we call amorphization, which means the mineral present in volcanic ash will be destroyed. And for any material to be suitable for using either as SCM or as a raw material to make geopolymer, it needs to have like a high amount of amorphous phase content. Amorphous phase means the crystal that have been destroyed or dismantled. So the material is easy to handle by any chemical. So by doing the mechanochemical activation of the volcanic ash, we obtain very interesting results, and I will be showing some of those results with you in my next coming slide. Here, for example, we have the effect of the mechanochemical activation on the particle size distribution of the volcanic ash. As we can see in this graph in the left, as one can see here on the left, when you ball mill volcanic ash for different time, you initially have a significant reduction of the size of the particle and then an increase with milling time. That is what we call here the recrystallization. on the agglomeration. And we can also see here how by milling volcanic ash at different time, we are able to minimize the amount of fine particle. And when you minimize the amount of particle, at the first is you increase the reactivity of the material. And the second stage, you are also able to change the mineral, the crystal structure of your materials. I mean, you are trying to destroy your material to make it amorphous, not have like a perfect pattern. It has to be like completely amorphous. So here I'm showing some of the results that I've obtained here. In this graph, this one, I measure like the heat of the reaction. What is it? Because when you mix cement with water, you will have heat being released. And the amount of heat that is being released gives information about the reactivity of the material and how good the material, the blended cement that you have is. Because more heat means more products are being are reacting in your system. So by the volcanic ash that has been activated for different time, we can see an increase of the heat of the reaction. Here, what I did is I mixed Portland cement with 25% of volcanic ash. So for the same milling time, and one can see that how the heat is increasing. The increase of the heat, what does it mean? It means that since I've only added 25%, since by activating my volcanic ash, I can have a more reactive volcanic ash, it means instead of adding 25% of volcanic ash in my blended cement, I can now add like 30 or 40%. That is beneficial. First, from the environmental point of view, because from this one, we are now able to substitute Portland cement with a higher percentage. The second thing is the more you substitute Portland cement, more durable your cement it is. So you have a cement which is more, you have a blended cement when you make concrete out of it, your concrete is very durable, very good. So the direct impact of it is mainly the decrease of the cost of the blended cement. As I said, cement is the most carbon intensive and the most expensive part in blended cement. So when you substitute cement with volcanic ash, for sure, you decrease the cost of the cement, which makes sense. And you also improve the property. So by doing the mechanochemical activation, we have been able to achieve this one, which is quite interesting for Africa, where we know the cost of the cement is more expensive. Cement is more expensive in Africa than in Europe, whereas the purchase power in Africa is by far lower than Europe or North or America. I know that this is, as I said, apart from blended cement, I've also used the same volcanic ash to make a geopolymer cement, which is produced from the process that I showed in one of the previous slides. This slide, for example, summarizes the changes on the particle size of the volcanic ash and the effect on the mechanical property. Here, this one was really fantastic because, as you can see here at the beginning, the volcanic ash that I used to make this geopolymer cement was not working at all. So by taking that volcanic ash, mixing with the alkaline solution, as I presented previously, I could not have a material that hardened. Even after 90 days, the material was still soft, which means that volcanic ash was not suitable at all to make a blended, to make geopolymer cement. But what happened is, by applying the mechanochemical activation, we can see that a material that was not able to achieve any strength, that was not able to harden even after 90 days, is now able to achieve 45 megapascal after 90 days. What I mean by 45 megapascal, this is quite huge. It means the product that are being developed here can even be used to construct bridge. You know, for bridge, you need material that are very strong. So that is quite fantastic. A material that was not able to give any strength initially, by applying this process, we have a material that when mixed with our alkaline solution can achieve very higher mechanical property. That was very fantastic. I will continue by showing some of the product that I developed. Here, what we have is a volcanic ash concrete block. I mean, I designed some big concrete and trying to cure it in different measure. And here, what you are seeing here is a durability test, because, you know, when you design a product, even if it had like a very high mechanical property, you need to check if the product can sustain to water, because we used to say in material science that any material that sustains to water can sustain to anything. So here we have this concrete block that we have made, and here what I did is I cured them in different way. A dry curing, as you see here, just mix them, and a wet curing. This is because we all know that in Africa, the main weather is rain and sun. So it is either it's warm, either it is I mean, there are too many rain. So because of that changes of waiting period and drying season, we need to make sure that the material that we are developing can sustain to that to that environment. But in Europe, they don't need it, because in Europe they have cold. Sometimes they have another test that they use. But in Africa, we generally try to set up this test as one of the conventional tests to check whether a material works or not. So in this graph, in the right side, I have tested the mechanical property of the concrete blocks that I have made and that I have cured in those two conditions. So the dry compressive strength is the compressive that is measured in this concrete block, and the wet compressive strength in red is the compressive strength measured from this one. One can see here that here, I mean, what you see here as a high binder and a low binder, it simply means that because for making concrete, you have, as I said, you have a binder, which is a glue, and you have now added with like sand and gravel. So if you add more binder, you will also increase the cost of your concrete. If you add low binder, you will also decrease the cost of your concrete. So to make our product, to make sure that the product is still sustainable and available for anyone, we try to check two mix design. A mix design where we have a high binder content, a mix design where we had a low binder content, to check how those mix behave in those different climatic conditions. So for the dry mechanical property, we still see that even after 120 days, the mechanical property are still increasing, and we have very good performance. And even when they are put into water, we can see, although the composition can decrease for some sample, but we still have something which is very interesting. So from this test, we are now sure that the product or the geopolymer sample that we're developing out of the volcanic ash are very good material that can be used for our conventional construction. Here, I'm just showing some product that have been developed out of the volcanic ash. You can see here it is black, and the previous one it was red, because volcanic ash, they have different colors. So here's a kind of the paving block and hollow block that we have made a sample to show up that, I mean, at least this is how our product can look like if they are being developed at an industrial scale. So the title of this presentation was Sustaining Africa Building the Power of Volcanic Ash. From all the data that I've shown now, the power of the volcanic ash relies on those different points. First, it is a regenerative material, so we can use it in different, I mean, when you use volcanic ash as a raw material for building, you can still, even after the end of the life of the material, the volcanic ash that has been used can still be reused to make the product, can still be used as a raw material. It is easy for exploitation. On the contrary to clay and all those materials, volcanic ash are generally open mine quarry. So when you extract volcanic ash, you don't need to dig the earth. Just, I mean, it's like a mountain that you just have to collect your sample. And the benefit of this one is when you collect the sample at this time, you are trying to recover the surface that have been occupied by the ashes after the volcanic eruption. So this will also make this the land or the villages that have been buried or occupied by the ashes after the eruption, we can still use them after exploiting the quarry. So which is quite fantastic. Another point of the power of volcanic ash is easy for processing, which means for milling volcanic ash is very simple. What the material that I have shown sometimes, for some of the material, even by just pressing with your hand, you can have like a very powder material already. So the energy required for milling the material is very low compared to the other raw material. Environmental friendly, as I said, it's an open mine quarry. So exploiting volcanic ash doesn't have bigger impact in the environment, because when you exploit volcanic ash, you are just trying to restore the land that has been occupied by the ashes initially. As I showed previously in the map, it is a material which is widely available and accessible. So this point form the power of volcanic ash, because very few material can have all those benefits. I will end my presentation with this slide and recommendation. For Africa, what we need is a material that encompasses all those key points. The first one, climate negative. So the building material that we need in Africa should be climate negative. It means the material should not have any harmful or negative impact for the environment. That is common from every part of the world. But the second point, which is cost effective. We know Africa is a developing country. We cannot develop our built environment. We cannot build our infrastructure if we still have a very expensive material. So we need to have a material that is cost effective. That is why a material like volcanic ash, which is widely available, accessible, easy to get, is very welcome. And the product that you are developing should provide a certain comfort. In Africa, we are suffering from excessive heat, mainly in sub-Saharan Africa. So the material that we need to develop should be able to provide a certain thermal comfort to the building. So we need to make sure that the material is quite comfortable for the population. And the last point is the availability. So the raw material to develop our building material should be available, and the building material that are being developed has to be available around the continent, because what makes cement expensive actually in the continent is the availability of limestone and the clay. Limestone is not quite available in the continent. And the second thing, we need some time to transport cement or limestone from very very far location to the plant. This is a very problematic issue. Also, the cost of the transportation in the continent is very high because we do not have good road. So we need to prioritize material that are locally available. So that is the end of my presentation. So I will thank you.
All right, that is fantastic. Thank you, Dr. Noel Jumbo, for this fantastic presentation. Yeah, we'll have a few questions that have come in, and I will show them on the screen so that you can respond to them. Okay, so this is the first question. Yeah, please just put your question on the chat box, all right, so that we can pick them. The world is now turning to green building to reduce energy consumption and waste production. It's using volcanic ash in line with this trend. And then the second one on that is how can we blend this technique with traditional building method for sustainability?
Yes, that's a quite fantastic question. For the first question, of course, the world is going for a green building. That is clear. And that is the main reason why we are pushing volcanic ash as one of the most sustainable materials. I have to mention that in the world so far, most of the scientists are most focusing on fly ash and slag or calcined clay. So they have very few knowledge, I mean, not knowledge, but they are not really interested on using volcanic ash. So we are still struggling to demonstrate that volcanic ash is a more sustainable material than calcined clay because, as I said, volcanic ash is a material that is easy accessible, and the energy required for processing volcanic ash is by far lower than calcined clay. I say for clay, you need calcine it to temperature to 600 and 700, sometimes 800. But volcanic ash, you don't need that. By just using a mechanical activation process, which is a normal mechanical activation process, which consumes less energy than the heat need required for the calcination, make the material to be a sustainable material. So we believe that volcanic ash has a key role to play in achieving sustainability in the world built environment in the world, if it is used properly where it is available. And for the second question that rely on the how can we apply this one with the modern with the traditional method for sustainability? That is a fantastic question too. I guess here you mean by using earth material, which is good. For the earth material that we are using in Africa, actually the technique used consists of milling by mixing earth and cement, because you need to stabilize the earth for it to have like some strength. So when you mix the earth and the cement, you have a stabilized block. That is what is commonly that's the common practice in our traditional building method. But now the point is that with the material that you have developed, when you use them as a binder to stabilize the earth, it works pretty fine. So to be able to combine the two techniques, we have done some work where the material that we have developed is used as a binder to stabilize earth. So that we have already done some work on it where we stabilize earth with the geopolymer that we develop, and it works pretty fine and perfectly compared to when you use cement. Yeah.
All right. Thank you very much. The second one, I want to know about the mechanochemical activation of volcanic ash. What about the energy consumption need to achieve the finest expected?
Yeah, that is Good question. Good question. Okay. In the conventional milling process, you have a jar, a big jar, and you have ball inside. You put your sample, and when you rotate, the ball we come together each other and interact with the material in the sample and reach the fineness. But the magic around the mechanochemical activation is the process that you use. So you will use the same energy that you use to grind the clay or to grind any type of material. But here what happens is in the mechanochemical activation process, the process is like when the jar that you are using, I mean the ball jar in which you are putting your material, when it is turning like in a clockwise, the ball inside will be turning in the reverse sense. So the fact that both are moving in different direction make that the energy within the material is very high. So you are still using the same energy for a conventional milling, but within your milling media, the energy is quite high because of the mechanism that is happening. So you will also hear the mechanochemical activation named as a high energy milling process. It doesn't mean that it consumes a lot of energy. It's simply that the energy in the jar is very high. That's why the impact that it has in the material at the end is also very powerful and very high. Yeah.
That's great. Okay, volcanic eruptions aren't very common in Africa. This would then mean that volcanic ash has to be imported to Africa. Therefore, using volcanic ash in cement would hardly be economical in Africa. In short or long term, what is your take on this? Very educating lecture. Thank you.
Okay, thank you so much. Thank you so much. Okay, as I said, we do have a lot of volcano in Africa, and we do have a lot of volcanic deposit in Africa. That is why we do believe that it's the material for the future, not only in Africa, also in other countries. In Africa, we do not need to import volcanic ash because, as I said, even though the volcanic eruptions are not happening quite frequently, but when it happens, the amount of ashes that are being released can be used over hundreds of years. In Cameroon, for example, since the independence, one of the cement companies are using the volcanic ash as a replacement in their product. And so far, they are still using it. And we now have more than 6 to 7 cement plants in Cameroon. They are still using the same. Even in Tanzania, even in Zambia, even in Kenya, those materials being used already as supplementary cementitious materials to make blended cement. So in terms of importation, we do not need to import the material because the material is already available in the continent. That's why we are trying to demonstrate how powerful it is for sustaining our built environment.
All right. That is great. Okay, number 4. As we all know, mechanochemical activation is really consumption energy. Okay, I think you have answered this, isn't it?
Yeah, I answer, yeah.
Yeah, you answered this already. Yeah, the last question I got from here, how does the use of volcanic ash in the construction materials contribute to the sustainability of buildings in Africa? And what are the potential environmental and economic benefits of this approach compared to traditional materials? Yeah, I think you have partly answered this, but I think you can still respond to this.
Yeah, it is a nice and tough question too. What I will say is like, can you show me the question again, please? Because I miss it.
Yeah.
Okay. When we deal with sustainability in the built environment, it relies on, I will say, 3 principles. First, we need a material that is climate negative, so it doesn't have a bigger impact in the environment. Secondly, we need a material that is available, not only for now, that will be also available for the 100 years coming. And the third principle is the cost of the material. So the material need to be cheaper. So I think in my presentation, I have tried to demonstrate that those 3 principles are met by volcanic ash because they are available compared to most of the raw material that's being used, like limestone or clay for making cement or everything. The exploitation of the volcanic ash is less, it's more environmental friendly than those materials because you do not need to change anything in the ecology. You do not need to change anything in the environment. The only thing that you need to do is to collect the material. And when you collect the material, you contribute to restore the land that has been occupied by the ashes after the volcanic eruption. That's what makes it an environmental friendly material. And the energy required for milling volcanic ash is also very less because when you have a material, the harder the material it is, the higher energy you need to mill the material to get a certain fineness. But with volcanic ash, in some places, you will even find them already in powder form in some places. So in that sense, it's a good material. I hope I asked this question.
Yeah, yeah, okay. I think those are the questions that came in, but let me ask. This is quite beautiful and encouraging. So why don't we start using it immediately? What is the situation in Africa now that we can't just start using this fantastic technology?
Yeah, I mean, that is a question that always come out when I present this thing. The point is that, as I said, in Africa, we need resources to implement those technology because we have been working in this material for already more than 10 years now, and we have got fantastic result and interesting result, but we are still missing to move from the lab to the industry because of the political situation, the economical situation in most of the African countries. So efforts are being made to try to at least set up a pilot plan where we can produce a hollow block or paving block for trying to commercialize. But at that age now, this is out of the control of the scientists. We are trying to make a kind of diplomacy with politicians if we can get funding to implement the material at a pilot scale. But that is the main issue that we are having now in Africa. And the second thing is like many of our our government in general in Africa, they are not like very they don't really take in serious what scientists are doing unless it comes maybe from abroad. So that is a need for that. Us as a scientist, we need to do a lot of effort to educate and to sensibilize all the government, the policy maker about what we are doing, for them to be able to see that what we are doing also is suitable for the country. So there are a lot of things that still need to do, but the main issue now is the lack of funding to move from the lab to set up a pilot scale, because we still need to demonstrate that it works at a pilot scale. Yeah.
Well, you answered lots of questions I wanted to ask you because now you were in Cameroon, but now you're in London. You enjoy yourself. Your life is easier, isn't it? You have the resources you need to do your research. Yeah, I mean, this is a problem. This is a problem because, one of the questions I had is there a political way to do this? Because as you know, one of the big players in the cement industry in Africa is Dangote.
Yeah.
It's Dangote. So if you have this type of technology with his current situation, it becomes difficult to convince him to go into things like this because of the political climate. Take for instance, he has built a refinery in Lagos, Nigeria. Come on, you see, we produce oil and crude oil, and we take it abroad to refine, and we bring it back, and we pay a huge amount of money, and then we begin to subsidize it, and it's involved in a climate of corruption. And Dangote had this fantastic idea, and he has built this in Lagos, the refinery, and it is launched. But this guy cannot even breathe. He can't breathe. It's a problem. And so with these fantastic ideas, it's really problematic really to see how we can move forward. Move forward. What I mean is that taking the ideas from the lab to commercialization. Last month, we had another presenter who, we spent lots of time trying to discuss this thing. And she has this idea, and I was asking her, so why are you still where you are? She said, they don't believe in me. I don't have money.
That's it.
Yeah, but now you are in London and somebody believes in you and somebody can give you money to do your research. What an irony for Africa. And the question is, looking at this product you have now, do you think you would tell a big story of what the revolution it has done in Africa in the next 50 years?
That is a challenging question. because actually we should. I just for the beginning, I just want to mention something. Actually, in Africa, I will say something that may shock most of the African. We do not produce at least cement. The whole process that I show, you will see that most of the cement company, including Dangote, they import clinker from Asia or South America or Europe. They import clinker and they grind it and they mix with some volcanic ash or calcine available in the country. That's also one of the reasons why we still have a very high price of cement in Africa. So this technology, at least if it is applied at a large scale, it will be like a paradigm shift from the way we are using the construction material. But we have to be realistic. It's not actually possible to use the material directly because we still need to go through the implementation of the standard and all those things. But at least we are already sure that the material works very fine. And the European people, they're already moving forward with the standardization of the material. So there's something that has to be done. I mean, the material, in technical point of view, we are sure that it may work fine. But the only thing that we are expecting from those big companies that they have to be aware that there is not a single technology that will save Africa. We need to combine many technologies together to achieve a certain level of development. Even the cement, actually, none of the African countries are like sufficient in the amount of cement that they use. They still have to import cement from abroad. So if you are able to bring in the market a technology, that will not directly replace 100% of the cement that is being used, but at least for any African to build his house, a small house, if he can have a cement ready-made for him, that will be less expensive. That will be a big shift in the continent. So our plan now is to use that material, not to replace 100% of cement, although we expect it to replace in more than 50 years. But at this time, we want the material to introduce the market slowly because we also know that we will face competition or we will face any challenges with the cement industry that will not maybe like this material to be introduced. You were saying, actually, with oil in Nigeria, that's the same in many countries. We produce oil, but we import oil. That's the same here. They import clinker that they ground. They prefer to import clinker because economically it's good for them. But for the continent, it's not good because the commercial balance of the continent is deficient. So we need to rely on those technologies. That is why we expect to have the support of those companies at least to develop the product. That's the main challenges that we have to face now. Yeah.
All right, ladies and gentlemen, I think you can see when we talk about ideas that make a difference. This night we have listened to our eminent brother and scientist, Dr. Noel Jobo, who has presented this fantastic product he and his team have been working on. Well, our hope is not only to hear these ideas, but to see how we can, continue to sound the bell as Africans until we get it right. Now he's in Imperial College in London. These innovations, before you know it, it is taken by the white men, and they use him, and because they understand the importance of these things. We hope that as a continent and as a people, we'll come to a point where we can capitalize on the opportunities we have. So, Dr. Jobo, thank you very much for this evening. We appreciate you. This is not the first time you're coming on board. You have been a friend of the house. So thank you for always making yourself available. And so we will call you when next we need you, and I believe that you will answer. So thank you for this evening. So ladies and gentlemen, before we draw the curtain, just join me in thanking our speaker for this night, Dr. Joel Jumbo. And let me tell you finally what is coming up next. You remember last month we had 2 presentations, but one had challenges with the network. But apart from that, we also were carried away with the presentation we had. It was quite fantastic that we just needed to give it time to exhaust the discussion. So we promised to bring the second speaker back in October, and that is the multi-power of date seeds. So I don't think you would like to miss this. If you like your health, if you like nutrition, if you like improvement in your meal, so we're going to have Mrs. Mona Gamma Idris, who will come to tell us. She has several products she's doing, and it's also a story of Africa. And we hope that you will join us on the 27th of October. Dr. Arnold's Research Tips and Tricks continues to the 31st edition, and we are looking at networking. You must be collegiate. 25th of October, please join us. To emphasize again, the bell is ringing, the clock is ticking for the ASFI second annual virtual conference and boot camp. Our speakers are all lined up and they are ready. Tomorrow ends the registration for early bird registration. So if you want to take advantage of reduced price to register, tomorrow is the deadline. And then tomorrow is also the deadline for submission of late-breaking abstract. I know that many of us do it the last minute, so we hope that you don't do it when your network is down. So please do it beforehand. It's a well-packed conference with several programs. We have some highlights here, and there are many programs behind the scene that you will see that there. So please join us in these 3 days of networking, collaboration, relaxing atmosphere, and hearing some of the things that will motivate us to do better as a people. Okay, to remind you again, the ASFI second edition, the time is coming. It is on GMOs. What is the need for Africa? Balancing innovation, African food system in modern agriculture. The team is ready, so please join us on the 11th of October. Remember, you have to register. The link has been flying around, so register and come to make your voice heard. It's just 1 hour, and then we are over with it. Yes, for the conference, we have announced this. If you have a product, if you have a platform, if you have your organization, you want to take advantage to promote it in the event booklet, it's free of charge. So we have sent this out. Just send it to conference 2023 at africansciencefrontiers.com. So please send it before the deadline, 31st of October, and we'll be happy to include your organization information in the booklet of the program. You never know who can be interested to collaborate or even to fund you. All right, so ladies and gentlemen, thank you for this evening. And of course, I always meet you before we start. Let me remove that if you want to add your voice this evening. And I wish you a very wonderful week ahead. Thank you for coming.
Thank you, Prof. Good night.
Thank you. Good night.
Yeah, Prof. Good night. Have a wonderful night.
Thank you. Thank you, everyone.
Good night. Blessed week ahead.
Thank you. Good night.
Thank you all.
Thank you. Good night.